Hi guys, my name is Dr. Sean Connolly, and in this video we're going to be discussing the topic of hypothesis testing. The material I'm using is taken from this book, College Statistics Made Easy by Dr. Sean Connolly, and it's available on Amazon.com. Okay, here it is. Here's the heading: Methodology for making a decision. Large sample case. We wish to develop a test procedure that enables us to either accept or reject H0. Such a procedure is called a test of hypotheses. Consider the following example, that of a court of law. In most jurisdictions, the defendant is presumed innocent at the start of the trial. Now, in this case, the null and alternative hypothesis given by H0, defendant is innocent, H1, defendant is guilty. All right. Now, how would you conduct a test in this case? Suppose blood is found on the defendant's clothes. This blood provides evidence which supports the alternative hypothesis of guilt. Yeah, look at H1, your alternative hypothesis, that is the defendant is guilty. Well, I found blood on the guy's clothes. Well, that supports the alternative hypothesis of guilt. Is any such evidence present in our CinemaGore's example? Thankfully, yes. Before providing this evidence, let's rewrite the null and alternative hypothesis below, because we might have forgotten what it is. Now remember, H0, mu is equal to 200, H1, mu is greater than 200. When the advertising campaign had concluded, a random sample of CinemaGore's was taken, and the average amount spent was found to be $212. Thus, the sample mean is $212. Now remember, it's a sample mean because it's a mean based on a sample of 150 people. Again, we like to replace everything with symbols. Let X bar denote the sample mean. Now we're going to be discussing the sample mean as we proceed. Just in your own head, when you see an X bar, you think it's the sample mean of 150 CinemaGore's. By the way, let's look up back here. See mu? I mean, what's mu, Sean? Mu is also a mean, but it's a population mean, the mean of everybody in the population. X bar is only a sample mean, the mean of 150 CinemaGore's. But anyway, back to this. Thus, the sample mean is $212. Let X bar represent the sample mean. Hence, X bar equals 212. X bar, the sample mean, and in this case, it's the sample mean of 150 CinemaGore's. Their average spend worked out to be 212. Recall from chapter 7 that the sample mean X bar is an estimator of the population mean mu. Mu is the population mean, the mean of everybody. X bar is only a sample mean. Well, obviously I'll use the sample mean as estimate of the population mean. All right, look at the alternative hypothesis now. Check it out. H1, mu is greater than 200. It claims that the population mean mu is greater than 200. The sample mean of X bar equals 212 supports this claim as its value is greater than 200. I would agree with that then. In fact, any value of the sample mean greater than 200 provides evidence that the alternative hypothesis is true. Well, that is true. Check it out. H1 says that the population mean is greater than 200. I got a sample estimate of the mean. It's 212. Yeah, that's greater than 200. That supports H1. Very good. Now, but is the evidence in hand, X bar equal to 200, sufficient for us to conclude that the alternative hypothesis is true? Is even more evidence required? All right, you might say, well, I'm a bit confused. Well, check this out. In the court example, blood found on the defendant's clothes supports the alternative hypothesis of guilt. However, more evidence may be required, perhaps in the form of a witness to the crime to conclude that the alternative hypothesis to conclude that the alternative hypothesis is true. In our CinemaGore example, although X bar equals 212 provides evidence that the null hypothesis is true, it may be inadequate to conclude that it is true. Maybe more evidence is required in the form of a greater value of X bar. Maybe X bar equals 290. In this section, we develop a test procedure for the large sample case, i.e. the case where a sample of at least 30 is taken from the population. So that's the definition of a large sample case. I take a sample of at least 30 from the population. You might recall we took a sample of 150, so therefore the large sample case is definitely applicable to us here. Later, we will address the case where a sample of less than 30 is taken. Okay. As the evidence involves X bar, we must obtain its sampling distribution. Now, from chapter 6 of the book, the central limit theorem states that for large samples, X bar is a normal variable with mean mu and variance sigma squared over n. Now, you mightn't have chapter 6. It doesn't matter. You can just accept that statement for now. So I know the sampling distribution of X bar. A sample is considered large if n is greater than or equal to 30. We stated that earlier. We took a random sample of 150 cinema cores. As we took a random sample of 150 cinema cores, we may invoke the theorem as follows. Check it out. All right. X bar, the distribution of X bar, it's a normal variable with mean mu variance sigma squared over n. Let's stick in some numbers. Let's look at the red writing. Sigma equals 50, provided in the question. Do you know if you go back and look at the original question, you'll actually find it states sigma equals 50. Well, if sigma equals 50, sigma squared is 50 squared. Calculator time. N denotes the sample size. Now, in this case, we took a sample of 150 cinema cores, hence n equals 150. Okay, now let's check this out. I'm trying to put in numbers here for these parameters. Now, I've got sigma, I've got n, but I don't have mu. So what value of mu shall we employ? Let's rewrite the null and alternative hypothesis. There they are. H0, mu is equal to 200. H1, mu is greater than 200. But what value of mu will I use? According to the null hypothesis, mu is equal to 200. Well, that is true. See there? Mu is equal to 200. But according to the alternative hypothesis, any value of mu greater than 200 is possible. So what value of mu shall we use? We will assume that the null hypothesis is true. Now remember that. You'll need that information going forward. We're going to assume, I don't know if it is true by the way, we're going to assume that the null hypothesis is true. Well, if the null hypothesis is true, mu is equal to 200. I'm going to use a value of 200 for mu. All right. Now look, that was the start. Look at this step. All we did was we stuck those numbers in for sigma, n, and mu. See? We stuck them in. We plugged in the values of mu, sigma, and n. Now guys, calculator time. 50 squared over 150 is 16.7. Pop it into there and we get, there it is. X bar is distributed as a normal variable with mu 200 and variance 16.7. A picture of X bar is shown below. You told me X bar is a normal distribution. There it is, the normal curve. Its mu is 200, so it's centered at 200. It sure is. And the variance is 16.7. Well, we just wrote that down beside X bar is 16.7. So that's the distribution of X bar. Now, let's have a look at this. We have obtained the sampling distribution of X bar on the basis that the null hypothesis is true, as we let mu equals 200. The random sample of 150 cinema cores yielded a sample mean of $212, i.e. X bar equals 212. Yeah, you might recall that. Let's obtain the chances of obtaining a value of $212 or more when the null hypothesis is true. That is, let's obtain, now look at the symbolism. Now this is all discussed in chapter 6. P stands for probability that X bar is greater than 212 when mu equals 200. The sought probability is shown below. There it is. Do you own this normal curve? I want to find the probability that X bar is greater than 212. Well, there's 212. I want to find the area in there. You might recall from chapter 5, area equates to probability. So the area in there equals the probability that X bar is 212. I want to find that probability. Okay. So we require the probability that X bar is greater than 212. Now, this is discussed in a previous chapter, I believe it's chapter 5. But just to give you a quick synopsis. Here we have a normal table, a standard normal table, which is found in any textbook. It's actually found in my book as well, the College Statistics Made Easy. But you know this table here at the back of the book? It's only applicable to a normal 0-1 variable, a normal 0-1. Do you know in our case, well actually, it's written on the screen. Let's have a look at point number 1. To obtain the probability that X bar is greater than 212, where X bar is a normal 200, 16.7, we must first reference the normal table, this table. However, we can't make use of this table directly. This is because this table is only applicable to a normal 0, 1 distribution. Now you might recall, the first number there is 0, corresponds to mu equals 0. The second number there, 1, corresponds to the variance of the random variable. To use this table, I must have a normal 0, 1. The mean must be 0 and the variance must be 1. Ah, but look, what do we have? We've got a normal 200, 16.7. The mean is 200, the variance is 16.7. Okay, we have a normal 200, 16.7 distribution. Please refer to chapter 5 for clarity on this point if you're a bit confused. However, we can make use of this table by converting, keyword converting, from a normal 216.7 distribution to a normal 0, 1 distribution. I can convert it. The population of cinema goers is considered an infinite population. In chapter 6 and 7, we stated that conversion formula for an infinite population is, there's our formula. There's our conversion formula. Now, incidentally, I just stated here the population of cinema goers is considered an infinite population. Again, if you look at chapter 6, that'll describe when an infinite population is applicable. But anyway, you can just accept, listen, I've got a normal distribution which isn't a normal 0, 1. I want to convert it to a normal 0, 1. Here is the formula for it. Okay, so you don't have to know the exact details of that, but if you do, just go back to previous chapters. Okay. Let's apply this conversion to the probability that x bar is greater than 212. Here we go. The probability that x bar is greater than 212 is equal to, now remember, we're going to use a conversion formula. There's our formula, people. X bar minus mu over sigma over root n. So here I've got, see the side? The x bar, I applied it. I went x bar minus mu over sigma over root n. And see on the 212, I apply the exact same formula. Minus mu all over sigma over root n. See? Use the conversion formula, minus mu over sigma over root n. So there we have minus mu over sigma over root n, minus mu over sigma over root n. I like the red writing, by the way. It shows what you're doing to one side, you're doing to the other side. Okay, let's go to the next line. Now, let me stick in actual values. Well, do you know the problem? Remember we assumed mu was 200. We said sigma was 50 and n was equal to 150. Let's stick in those numbers. And we did. We stuck them in there. See the mu, replaced by 200, the sigma by 50, the n by 150. Now, let's go to this line. All this quantity, by definition, is z. And this I just replaced down here. Calculator time, people, equals the probability z is greater than 2.94. All right. Once you get to a z, that stands for a standard normal variable. It allows me to go to this table to look up the probability. Okay, so let's go on to the next step. We can now use the standard normal table to find the probability that z is greater than 2.94. Plain man's English, I can look up this table. First, let's draw a picture to aid us in obtaining the probability. We require the shaded area showing below. There it is. Referring to the normal table, in other words, I just looked up this table, we obtain the probability that z is greater than 2.9. The probability that z is greater than 2.94 equals 0.0016. Now here it comes, people. Thus, the probability that x bar is greater than 212 equals 0.0016 when mu equals 200. That's what we did in this step up here. See this step? We want to find the probability that x bar is greater than 212. Well, that's equal to the probability that z is greater than 2.94, and we're just after finding out that the probability that z is greater than 2.94 is 0.0016. Thus, the probability that x bar is greater than 212 equals 0.0016 when mu equals 200. This probability is very small. It was obtained on the basis that the null hypothesis is true, i.e. mu is equal to 200. Yeah, remember, we didn't know what value to put in for mu. So what we did is we assumed that the null hypothesis is true, and the null hypothesis stated that mu is equal to 200. Okay. Now, since this probability of 0.0016 is very small, the basis on which it was obtained is unlikely to be true, i.e. it's unlikely that the null hypothesis is true. Based on this reasoning, we choose to reject the null hypothesis that mu equals 200. That there is the crux of hypothesis testing. Let's see, did you catch it? Let's go back to here again. The probability that x bar is greater than 212 is 0.006 when mu is equal to 200. You see this probability statement? We worked it out assuming that mu is equal to 200. Now we don't know whether it was correct or not. But you know the result? This probability is very small, 0.0016, tiny. It was obtained on the basis that the null hypothesis is true, i.e. that mu is equal to 200. Since the probability is very small, the basis on which it was obtained is unlikely to be true. It's unlikely that the null hypothesis is true. Based on this reasoning, we choose to reject the null hypothesis that mu equals 200. I love that paragraph, people, because that explains the logic of hypothesis testing. Okay. Now, what to call a good bit of detail there, people. Let's see, can we recap on the logic again? Okay, let's quickly recap on the steps we employed in this testing procedure. We start by restating the null and alternative hypothesis. There we have it. H0, mu is equal to 200. H1, mu is greater than 200. You might recall mu represented the English words, the average amount spent by cinema goers equals 200. Okay, now, when the advertising had concluded, a random sample of cinema goers was taken, and the average amount spent was found to be $212, i.e. X bar is 212. You might recall, X bar is the sample mean. Incidentally, mu is the population mean. Look at the alternative hypothesis now. Check it out. Oh yeah, alternative hypothesis, mu is greater than 200. It claims that mu is greater than 200. The sample mean of 212 supports this claim, as its value is greater than 200. In fact, any value of the sample mean greater than 200 provides evidence that the alternative hypothesis is true. But how much evidence is required to conclude that it's true? To address this question, we obtain the chances of obtaining a value of $212 or more when the null hypothesis is true, i.e. we obtain the probability that X bar is greater than 212 when mu is equal to 200. I keep stressing when, because at this point, I don't know if it is equal to 200. Remember, we assumed H0 is true when H0 states that mu is equal to 200. Now, we found the probability that X bar is greater than 212 is 0.0016 when mu is 200. As this probability is very small, the basis on which it is obtained is unlikely to be true, i.e. it is unlikely that mu equals 200, and therefore we must conclude that the null hypothesis is false. Bang! We rejected H0 as the probability X bar is greater. Now that now actually has really given us a great understanding and logic of the rationale underlying hypothesis testing, the rationale for making a decision to either reject or accept H0. Now let's read on. We rejected H0 as the probability that X bar is greater than 212 equals 0.0016 is very small. However, how small is small? A researcher might suggest that 0.0016 is not small enough, or that it's too small. We need a cutoff value, i.e. a value that is typically accepted as small by researchers. Do you know, in my own mind, 0.0016 is very small, and therefore I would reject H0. But one man's small might be another man's big, so we need a cutoff value. Typical values used in practice are 0.1, 0.05, or 0.01. In this example, we will opt for a value of 0.05. So that would be our definition of small. If it's less than 0.05, I'm going to reject H0, because I'm going to say the probability of it happening is tiny. But if it's above 0.05, then I will say, oh, I won't reject H0. Let's go on. And people, there we come to our end of our video. Now, there's a lot more discussion about hypothesis testing in the book. And again, I've just put it up here, College Statistics Made Easy by Dr. Sean Connolly, and it's available on Amazon.com.